We know that acceleration is given by a change in velocity over change in time. Okay, so as a vector, we care about the vector change and saw that the acceleration could be non-zero if it's speeding up or slowing down, or if it's changing direction. Now I want to go into that direction change a little bit more and see that we can also interpret the acceleration itself as causing either a change in direction or a change in speed. So let's take a case where we have a particle just traveling to the right there. Let's say this is V initial. Okay. And at that moment in time, there's an acceleration downward. Okay. Now besides the scaling of time, we can say that this is basically proportional to the change in velocity. So if I take this tip, or take this and move it to the tip over here, okay, and say that's basically our change in velocity, our acceleration times time, then I can find my final velocity to be that vector. Okay, we add the change to the initial to get the total. Alright, so let me, just to clarify, that is acceleration times its time interval. Okay, so this would be over, some time period. What do we see here? Well, this is a hypotenuse to a right triangle for this case where our acceleration was perpendicular to the initial velocity. That means that this length here must be bigger than that length. So we sped it up. Final velocity is a greater magnitude than initial velocity. So we were able to speed it up. But we also are changing direction. Instead of pointing just to the right, it's got a part to the right and a part now pointing downward. And so we've changed its direction as well. Okay, so that might say, well, this acceleration changed both speed and direction. Indeed, it would have for this time period we chose. But what if we choose a smaller time period? Okay, so we choose a smaller time period, which means this change got a lot smaller. Okay, so if I make that much smaller, here's my initial, and this gets much smaller, then my final looks to be like that. Okay, and still I have a change in length here. This hypotenuse is now still bigger than this, but it's not very much at all. Okay, so if I take that argument and go further and say let's go even smaller time, a very, very small amount of time, so it's just really at a moment, at one moment in time the acceleration is perpendicular to the velocity, then this side right here gets super small, such that these are pretty much the same vector, and so they are parallel. So no matter how big this acceleration is, because the time period is so small, I'm focusing at just one moment, that this perpendicular acceleration caused only a slight change in direction. Okay, and we could build on that and emphasize that for any motion, a perpendicular acceleration for that moment will change only the direction. Now the reason why this is hard to grasp is because over a short period of time this was perpendicular to this velocity, but it's not perpendicular to that one, and so that's why we have a change in speed as well. But if the acceleration always is perpendicular to the motion, then it can only change direction, and we see that for circular motion, what we call uniform circular motion. So if this is a perfect circle, obviously I'm not drawing a perfect circle, but this is a perfect circle and it's moving at constant speed, then everywhere the acceleration would be pointed perpendicular to it or radially inward. Okay. At each one of these points we could draw two vectors, one coming in and one coming out, and we'd find that vector is bisecting those two. And if we make those vectors small enough, kind of like what we did here, this will end up being perpendicular to the tangent of that line. That can be applied to anything. So if we do have some acceleration that, let's say here's our velocity vector again, we have an acceleration vector then at that moment of time, sorry, vector here, at that moment of time, this acceleration can be broken into a perpendicular part that changes direction only. I'm going to draw A with a perpendicular symbol. That means a perpendicular part. And it can be broken into a part that is parallel to the motion. Okay, and that is what's responsible for causing this to speed up or slow down. So this is any acceleration for any time period in fact works, but the acceleration, this piece is for that one moment where it's perpendicular to that speed. And again, in a circular motion, then that acceleration, there is always a perpendicular acceleration there. So we now can say our acceleration is equal to a perp, or a perpendicular plus a parallel. This one changes direction, and this one changes speed.